Good afternoon, everyone. In the last lecture, we discussed about the work, right? Complete the concept of work, right? Then we started with the concept of energy, right? There were different types of energy that we were discussing. The first kind of energy that we discussed in the last lecture was the mechanical energy, right? In mechanical energy, there were two types of energy that we discussed. One was the kinetic energy, another was the potential energy, right? So we know that kinetic energy is because of the motion of a body, right? And potential energy is by virtue of a position of a body, right? We'll be discussing both types of energy in bit detail, right? One by one. So in the last lecture also we discussed about the kinetic energy that's given by the half mv square, right? That's given by the half mv square. So kinetic energy of a particle is given by if v is the speed of the particle, then the kinetic energy of the particle is half mv square, right? This is the kinetic energy of the particle, right? So we also discussed that kinetic energy can be also written as p square momentum square upon 2 times the mass of the body, right? Now let's apply this equation to calculate try to solve these questions, right, one by one. So the first question is that if the linear momentum of a body is increased by 50%, then by what percentage will its kinetic energy increase, right? So we have to find increase in the kinetic energy, right? So it means that if initial energy is K is the initial kinetic energy, right? K1, you can write it as P square upon 2m. Now momentum has been increased by 50%, right? By 50%, we mean that by 50% increase in the momentum, it means that the final momentum has become equal to P plus 50% increase of the initial value. That's 50 upon 100 multiplied by P, right? It will be nothing. It will be 3P upon 2, right? 3P upon 2. This will be the final momentum, right? So the final kinetic energy K final will be nothing. It will be equal to, once again, final momentum square upon 2m, right? That will be 3P by 2 whole square upon 2 as the mass of a body, right? So it will be 9P square upon 9P square upon 4 into 2m, right? That's equal to 9P square upon 8m, right? 9P square upon 8m. Now the change by percentage change in its kinetic energy will be nothing. Percentage change in its kinetic energy will be the change in kinetic energy upon the initial kinetic energy multiplied by the 100, right? This will be the percentage change in kinetic energy. So final kinetic energy is nothing. It's 9P square upon 8m. It's 9P square upon 8m minus initial kinetic energy, that's P square upon 2m. Right? This is the change in kinetic energy upon the initial kinetic energy. That's P square upon 2m. Now from here, P square, and P square will get cancelled, right? M, and M will also get cancelled. And we have to multiply it by a factor of 100, right? To calculate the percentage change in kinetic energy, right? So it will be 9 upon 8 minus P 1 upon 2, right? We can write it as, it will be 8 will be the LCM for 8, right? So we'll be left with 9 minus 4, right? 9 minus 4 upon 2. It will be 5 upon 5 into 2 5 into multiplied by 100, right? Upon 8, right? So it will be equal to 1000 upon 8, right? That's equal to 125. 125 means that the percentage change in the kinetic energy will be nothing. It will be equal to 125%. So 125% will be the change in the kinetic energy, right? Similarly, in the next question, if we look at this question, the kinetic energy of a particle is increased by 300%. Find the percentage change or the percentage increase in its momentum, right? So initial kinetic energy is given as that's p square upon 2m, right? P square upon 2m. And the final kinetic energy is given as p square upon p final square upon 2m, right? Now the question is that we have to find the percentage change in percentage if the kinetic energy is increased by 300%. Find the percentage increase in its moment. Let's suppose if we double the momentum, initial momentum, right? That's 2p. Then the final kinetic energy will be nothing. It will be 4p square upon 2m, right? 4p square upon 2m, right? And the percentage change in the kinetic energy will be equal to delta k upon k multiplied by 100. This will be the percentage change in kinetic energy. That will be equal to 4p square upon 2m minus p square upon 2m, right? And divided by the initial kinetic energy, that's p square upon 2m, right? P square upon 2m will get cancelled, right? We'll be left with only uh, 4 minus 1, right? We'll be left with only, yes, 4 minus 1, that's 3, right? Multiplied by 100, right? By a factor of 100, right? Now this is nothing, this is 300%, right? This is nothing, this is 300%. It means that if we double, the momentum, the kinetic energy changes 300%. It means that the percentage change in momentum is 100%, right? So the percentage change in momentum is 100%. So delta p upon p is p on initial momentum, that's also p, right? Multiplied by 100, that's equal to 100%. So 100% will be the change in momentum. Then there will be 300% increase in its kinetic energy, right? Now let's move on to the very important concept, right? That's the work energy theorem. So what work energy theorem says that work energy theorem states that whenever a kinetic energy, whenever a work is done on a body, right? Whenever a work is done on a body by applying some force, that work actually changes the kinetic energy of a body, right? Be it work done by the conservative forces, be it work done by any force, be it non-conservative force. So work done by any force is actually nothing. That's equal to the change in kinetic energy. So we can write work done by all forces, right? Work done by all forces. That's given by the change in kinetic energy, right? This is nothing. This is what we call as work energy theorem, right? It's a very important theorem. Work energy theorem. Work energy theorem. So work energy theorem states that work done by all forces on a body always is equal to change in the kinetic energy of a body, right? That's always equal to the change in kinetic energy of a body. Let's try to see it. Let's suppose force F is acting on this body. If force F acts on this body, right? Then its speed velocity change from u to v, right? This is the initial velocity, right? This is the initial velocity of this body, and this is the final velocity, right? This is the final velocity, right? Let's suppose the constant force is acting on this body, right? Constant force equal to F, right? Constant force is equal to F, right? We know that V square is equal to U square, right? Plus 2AS, right? Or we can write it equal to V square minus U square upon 2A, that's equal to S, right? Where S is the displacement. So from position A to position B, the displacement of this body is S, right? Now, we know the force is F, or we can say acceleration is nothing force upon mass, right? It's force upon mass, right? We can place this acceleration with force upon mass, right? We'll be left with V square minus U square upon 2s F, right? Multiplied by the factor M here, right? That's equal to S, right? Now, we can also write it as half M V square minus U square, that's equal to F into S, right? Now this F into force into displacement is nothing. This is the work done, right? This is the work done. This is the work done in displacing a body by a displacement of S, right? So this is the work done, right? W. And you can see here, this work done is nothing, this work done is nothing. This work done is equal to half m v square minus half m u square, right? And this half m v square is nothing. This is the final kinetic energy, K final minus K initial. That's equal to change in kinetic energy. That's delta K, right? The work done by any force, and this was the work done by any force, be it variable force, be it constant force, it's always equal to the change in kinetic energy, right? It's always equal to the change in kinetic energy, right? We can also calculate this theorem for the variable force as well, right? For the variable force as well. If the force is variable, still we'll get the same answer. That's the change in kinetic energy. Let's suppose uh, for the variable force, the work done is nothing. It's integral of f dx, right? Integral of f dx. So we can write it as integral of m a dx, right? M a dx, because force is mass into acceleration. So our m a we can write as v dv over dx, right? dv over dx multiplied by dx, right? So from here, this and this will get cancelled. I will integrate it from u to v, right? U to v. So integration of v with respect to v will be nothing. It will be v square upon 2, right? With the limits u to v, right? It means the work done will be nothing. Work done will be equal to half m upper limit minus lower limit. That's v minus u, right? V square minus u square. This is nothing. This is once again change in kinetic energy, right? This is nothing. This is once again a change in kinetic energy. So it means that work energy theorem states that work done by any force, be it constant force, be it variable force, be it conservative force, or be it non-conservative force, it's always equal to the change in kinetic energy of the body, right? So this is how we calculate the work done by any force, right? So if we calculate the change in kinetic energy in the body, we'll get to know about the work done on the body, right? Now let's try to solve a question on this, based on this theorem. You can see in this question, a force applied on a particle of mass 2 kg changed its velocity from 2 I cap plus 3 j cap, 2 I cap plus 6 j cap meter per second to 3 I cap plus 4 j cap meter per second. We have to find the work done in the process, right? So velocity has changed, right? Velocity has changed. That's given as if initial velocity we calculate magnitude of the initial velocity, that will be equal to, it will be equal to under root of 2 square plus 6 square, right? So it will be 36 plus 4, that will be root 40, right? Root 40, right? Or we can write it as 2 root 10. We can write it as 2 root 10 meter per second. 2 root 10 meter per second. Similarly, the final velocity, magnitude of the final velocity will be nothing, or we can say the final speed is root of 3 square plus 4 square, right? That will be equal to root of 25. That will be equal to, right, 5, right? That will be equal to 5. So the 5 meter per second is the final speed or velocity, right? Final velocity, right? Now the work done will be nothing. Work done will be given by the change in its kinetic energies, right? W will be equal to delta K, right? That will be equal to half m. That's equal to 2 kg, right? V square minus u square, right? So V square is actually final square, that's 25, and the initial square, that is 40, right? 40, right? That's equal to 40. So it's actually equal to, so it has to be final speed is root 40, right? And initial speed is root 40, right? And the final speed is 5, right? So it will be equal to 2 and 2 will get cancelled. It will be equal to minus 15 joules, right? It means that the kinetic energy of this body has actually decreased. It means work has been done on the system. The work done on the system is a negative work, and the kinetic energy has decreased for the system, right? Now, similarly for this question as well, we can apply the work energy theorem, right? You can see at this the displacement x of a body of mass 1 kg on a smooth horizontal surface, right? The displacement x of a body of mass 1 kg on a smooth horizontal surface as a function of time is given as x is equal to, it's given as x is equal to t cube upon 3, right? It's a t cube upon 3, right? So it's actually t cube upon 3, t cube upon 3, right? where x is in meters and t is in seconds. Find the work done by the external agent for the first 1 second, right? We have to calculate the work done by the external force for the first 1 second, right? Now we can once again apply the work energy theorem. That's work then is nothing. It's equal to change in kinetic energy, right? Change in kinetic energy, that will be equal to final kinetic energy minus initial kinetic energy, right? Now calculating the change in kinetic energy, first of all we'll try to calculate the speed, right, as a function of time. So we'll take the first derivative of x with respect to time, right? It will give us speed, right? It will be 3t square upon 3, right? 3t square upon 3. So that will be equal to t square. So this will give us the speed of this body at any instant, right? Speed of this body at any instant. So at t equal to 0, the value of p is, the value of initial speed is, right? Initial speed is 0, right? Because at t equal to 0, v is 0, right? Similarly, at t equal to 1 second, we have to calculate the, for the first 1 second. So t equal to 1 second, the final velocity of this body is 1, right? That's 1 meter per second, right? Now calculating the initial kinetic energy is 0, and the final kinetic energy is half m v square. That's 1 square, right? That's equal to half, right? That's equal to half. Therefore, the work done will be nothing. That will be equal to delta K, right? That will be equal to final kinetic energy. That's half minus initial kinetic energy. That's 0. So half joules or 0.5 joules is the answer for this question. It means that zero point 0.5 joules work has been done in displacing this body, right, for 1 second. Now let's move on to the very important concept. That's the concept of conservative and non-conservative forces, right? It's a very important concept. So conservative forces, let's talk about the conservative forces. A force is said to be a conservative force if the work done by the force is independent of the path and depends only initial and final positions, right? And it does not depend on the nature of the path followed between the initial and the final position. This is the importance of the conservative forces. It means that you can see here, if we are displacing a body, right? If we displace a body from position A to position B, right? We're displacing the body here from position A to position B, right? Through different paths. We're displacing this body from position A to position B through different paths. There is path 1, there is path 2, there is path 3, right? There are three paths of three different natures, right? Three paths of three different natures, right? Three paths of three different natures. So you can see here, we can take this particle along this path A, we can take this particle along this path B, part 2, and we can also take this particle from position A to position B along this path 3, right? Along this path 3. Now, if the work done through all three different paths is W1, W2, and W3, right? In case of conservative forces, all these work done will be actually equal, right? They will be equal because the work done in case of conservative forces, it will be independent of the nature of the path, right? It will be independent of the nature of the path. It will only depend upon the final position and the initial position, right? It means that if the final position and initial position is same, if the final position and initial position is same, and initial position is same, then work done has to be same, right? Then work done has to be same in case of conservative forces. In case of conservative force. So if the force is non-conservative, then this work done may not be equal, right? This work done will not be equal. It will depend upon the path followed, right? For different paths, the work done will be different for the non-conservative forces, right? So these are the this is the concept of the conservative forces, right? So in case of conservative forces, work done is independent of path. One more important point about the conservative forces is that, let's suppose if we take a particle from position A through this path and back to its own position, right? Back to its own position, right? We're taking this particle in this closed path, right? This is a closed path, right? So in case of closed path, in the presence of conservative forces, right? In the presence of conservative forces, the work done in a closed path is always equal to zero, right? The work done in a closed path is always equal to zero. Work done in a closed path, work done in a closed path is zero, right? In conservative forces, right? So work done in a closed path is zero in conservative forces. It means that if force F is acting on this particle, the integral of F dot dl in a closed path, that will be equal to zero if F is conservative. If F is conservative. If force F is conservative, then integral of closed integral line integral of force will be equal to zero, right? And similarly for the non-conservative forces, right? In case of non-conservative forces, work done is actually a path dependent, right? It depends upon the path. It depends between between the initial and final position. It means that if we let's suppose this is the point A, right? This is the point B, right? This is point A and this is point B. Now, between point A and point B, if we take this particle through different paths, this is the path first, right? This is the path first, and this is the path second, right? This is the second path, and this is the third path, right? This is the third path, right? So let's suppose W1 is the work done here, and W2 is the work done here, and W3 is the work done here. So if the force acting on this particle is a non-conservative force, right? Then the work done by the non-conservative force will depend upon the path followed, right? It will depend upon the nature of the path followed, and it will uh, the work done through different paths will be different, right? Work done through different paths will be different. It means that W1 will not be equal to W2, right? Will not be equal to W3 in case of non-conservative forces, right? In case of non-conservative forces. And one more important point in case of non-conservative forces is that the work done in a closed path, right? Work done in a closed path is not equal to zero, right? The work done in a closed path is not equal to zero. It means that if we take a particle in a closed path with the help of some force, right? And the force is non-conservative in nature, then in that case, work done in a closed path will not be equal to zero. It means that line integral of force, right? F dot dl will be equal to, it will be a non-zero, right? It will be a non-zero. So it will not be a zero in case of non-conservative forces, right? So non-conservative, in case of non-conservative forces, the work done in a closed path is actually non-zero, right? That's not equal to zero. Now there are certain properties, right, that we'll try to see with respect to the what we call as conservative forces, right? The first concept is that if we differentiate between the two forces, that's the conservative and the non-conservative forces, we can see here the first differentiation lies work done does not depend upon path in case of conservative forces, right? And in case of non-conservative forces, the work done actually depends upon the path followed, right? And the second point is that work done in a round trip. It means work done in a closed path. In a conservative forces, right, is zero, right? For example, the conservative forces, you have gravitational forces, a conservative force. All the central forces are conservative forces, and spring force, it's also a conservative forces, right? These are some of the examples of conservative forces, right? Friction force or air drag, that's the non-conservative force. And the work done in a round trip or closed path in case of non-conservative force is not zero, it's non-zero, right? And very important point with respect to the conservative force is that when a conservative force acts within a system, the kinetic energy and the potential energy actually can change, right? Can change. However, there's some of the mechanical energy of the system does not change. It means the total mechanical energy of the system in a conservative forces remains conserved, right? Remains conserved. But that's not the case in case of non-conservative force, right? That's not in the case of the non-conservative force. It means that if the total sum of the kinetic energy and the mechanical energy in case of conservative force is conserved, it means that work done is actually completely recoverable, right? It's completely recoverable. It means that kinetic energy can get converted into potential energy, right? And potential energy can once again get converted into back into kinetic energy. So the concept of potential energy is only in case of conservative forces, right? In case of conservative forces, where the concept of potential energy, the concept of potential energy is not there in the non-conservative forces, right? And in case of conservative forces, both kinetic and potential or mechanical energy can interchange, right? So that the total mechanical energy is always conserved in case of conservative forces, right? But in case of non-conservative forces, the total mechanical energy is not conserved, or we can say the work done is not completely recoverable, right? In case of non-conservative forces. So these were the two important differentiation between all such forces, right? Now, talking about the potential energies, right? Talking about the potential energies, the energy possessed by a body by virtue of its position. And we also discussed that the potential energy is always associated with the conservative forces, right? It's always associated with conservative forces, right? It means that whenever there is a conservative force, work done can be stored in the form of a potential energy, right? So energy, potential energy is nothing. It's the energy possessed by a body by virtue of its position or configuration in presence of a conservative field, right? Potential energy, it depends upon the reference, right? It depends upon the reference that we are choosing for the potential energy, right? Or we can say that it's a relative quantity, right? Potential energy itself is a relative quantity, and it's only defined for the conservative fields, right? So it means that let's suppose if we have the gravitational field, right? This is the earth, and the gravitational field is a conservative field, right? It's a conservative field. Now if we take this body to some height h, right? To some height h here, right? To have some height h, body of mass m, then we are doing the work on this body. Right now this work done will be stored within the system as a potential energy, right? So this potential energy will depend only on the position of this body, right? It will only depend upon the position of this body. Let's suppose if we're taking this as the reference, it means we also discussed that potential energy is a relative quantity, right? It depends upon the reference. And for this reference, we're taking the potential energy to be equal to zero, right? We can take the reference as the center of the earth as well, but we can take also this as surface of the earth as the reference as well, right? So for height h from the surface of this earth, and the potential energy stored in this body will be equal to mgh, right? It will be mgh, right? Now, since this is a conservative field, now if we take this body of mass m, right, like this, to the same height h, right, to the same height h, right, to the same height h, and we have taken this body through a different height, right, through a different path, by same height h. Now the potential energy once again stored will be equal to mgh. So it will not depend upon the path followed, right? It will only depend upon the initial and final position of this body, right? Or we can say height of this body from the surface of earth, right? So that's the potential energy. So it once again shows that it's a conservative force, right? And its potential energy will not depend upon the path followed, right? It will only depend upon the initial and the final configuration of the body, right? So potential energy is a relative term, right? It's clear from this example, right? Now, one more important point is that we said that potential energy is defined for conservative force or conservative field. So there must be an important relation between them, right? Between the conservative forces and the potential energy, right? So any conservative force, any conservative force is always the negative gradient of uh, potential energy, right? So F is equal to minus gradient of U, right? U. So it means that if we take the derivative of potential energy with respect to its position, then we will get the force in that in the direction of that coordinate, right? It means that if we write this, the value of this grad is nothing. It's equal to del U upon del X, right? I cap plus del U upon del Y J cap plus del U upon del Z K cap, right? Right? Or we can write this force equal to conservative force, that's equal to minus times del U upon del X I cap plus del U upon del Y J cap and del U upon del Z K cap. This equation we also discussed in case of electrostatics, right? We'll discuss this equation in case of electrostatics as well in class 12, right? So here the force equation is minus del U upon del X I cap, right? This will give us the X component of the force, this will give us the Y component of the force, and this will give us the Z component of the force, right? So this is the important relation between the conservative force and the potential energy, right? Now let's solve this question and apply this concept in this question, right? To calculate the different quantities here. You can see here the potential energy of a conservative force system is given by ax square minus bx, right? The potential energy here is given as U is equal to ax square minus bx, right? So the potential energy of the system here, that's given here as ax square minus bx, right? It's given as ax square minus bx, right? Where A and B are constants, right? A and B are constants here. We had to find the potential expression for force and potential energy, right? We have to find the expression for force and potential energy at equilibrium, right? So it means that to calculate the expression for the force, we have to take the derivative of this potential, right? So F will be equal to nothing. It will be minus del U by del X, right? Minus del U by del X. We'll take the derivative of this equation, right? Derivative of this potential energy. That will be equal to ax square minus bx, right? So we can write it as minus 2ax, right? Plus b, right? Plus b. But this will be the value of the force, right? This is the expression for the force, right? You can see the force here is position dependent, right? Now, potential energy at equilibrium, right? Potential energy at equilibrium. So at equilibrium, the force on the body will be equal to zero, right? At equilibrium, the force on a body will be equal to zero, right? At equilibrium, the force on a body is equal to zero. F is equal to 0, right? It means that minus 2ax plus b has to be equal to 0, right? So from here, the value of x will come out to be b upon 2a, right? B upon 2a. So we have to calculate the potential energy at equilibrium. It means that we have to calculate the potential energy at x equal to b upon 2a, right? Now let's put this value in the potential energy equation. That's ax square. We can write it as b upon 2a whole square, right? Minus bx minus b into b upon 2a, right? So it will be equal to a times b square upon 4a square, right? Minus b square upon 2a. A and a will get cancelled. We'll be left with b square upon 4a minus b square upon 2a. That will be equal to minus b square upon 4a. So this will be the potential energy, right? This is nothing. This is the potential energy at equilibrium, right? Potential energy at equilibrium. This will be nothing. This is the potential energy at equilibrium. So this will be the potential energy of the system at equilibrium, right? Now talking about the gravitational and spring potential energy, right? We know that in case of gravitational force is also conservative force, right? So the work done with for the system will be stored as the potential energy, and it will only depend upon the initial and the final configuration, right? So if we are taking a body from height to a height h from the reference. If this is the reference point, then the potential energy here will be taken as 0, right? And the potential energy of the system, right, it will be nothing. It will be stored as the, that will be equal to mgh, right? It will depend upon the mgh for small heights, right? For small heights, for small heights, for small heights, right? uh, once we uh, Once we study the gravitation, right, we'll see how actually the potential energy varies with the position, right? For different heights, the potential energy will be different, right? So we'll study the actual relation for the potential energy there as well, right? So a potential energy will be here equal to mgh, right? We are taking g to be a constant here, right? G to be a constant here. Otherwise, as we move up, right, as we move up, the value of the potential, the value of the acceleration due to gravity changes with the height as well, right? So potential energy here is mgh, where g is a gravitational constant. It has to be taken as 9.8 meter per second square, right? For the small heights, we'll be using this equation, right? Now, similarly, in case of spring, right? In case of springs, the energy is stored as the potential energy. It means that, let's suppose this is the spring block system here, right? Or let's suppose this is the spring, right? This is the spring. And if we extend this spring with the help of some external force, then for the extension of this spring, right? For the extension, small extension of the spring, right? Small extension of the spring, right? Let's suppose dx is the extension, right? Dx is the extension. And the force developed in the spring is nothing. It will be equal to F is equal to minus kx, right? Right. This is the force developed in this spring, right? And this force is a conservative force, right? Spring force is also a conservative force. And the work done by this conservative force will be actually stored as the potential energy within this spring, right? And that potential energy of the spring, we can calculate integral of f dx, right? Integral of f dx, right? And this potential energy will be equal to half kx square, right? Half kx square. So if where x is the extension, right? Where x is the extension in the spring, right? Extension in the spring. So it will only depend upon this potential energy stored. Spring potential energy will depend upon the extension in the spring, right? How much the extension is within the spring, right? Half kx square will be the potential energy, right? So x is equal to extension in the spring. So this is the potential energy stored in the spring, right? So we studied about the gravitational potential energy and the spring potential energy, right? We'll be doing some questions in the next class with respect to these two forms of the potential energy, right? Then we'll be starting with the concept of power, right? So that's it for today. We'll meet in the next class.